Hello everyone, I'm Tomas Apeltauer and I work at Brno University of Technology and also at a small engineering company, Recognity, supporting Pathfinder and Prescriptive users in Czech Republic and Slovakia. I'm really glad being here and would like to talk about one of our several big projects here in Czech using pedestrian or fire simulation. Several months ago, we applied a risk analysis on the main railway station in Prague using the micro-simulation pedestrian model in the field called soft target protection. We are not able to publish the full results or specific measures for security managers, but I hope the following minutes will serve as a use case demonstrating the Pathfinder capabilities for this issue. Fire safety in the Czech Republic uses primarily a set of prescriptive codes which have been gradually improved for decades. These codes are designed to enable the civil engineer to make a basic assessment of the fire safety of a building without specific technical requirements. Simply speaking, the assessment must be possible for an old-school engineer with a paper project, a pencil, a notepad, and something for calculation. These codes are a simplified view of the behavior of people in the building. You can see here a comparison of this behavior of two identical groups of people in the same geometry. The upper simulation applies parameters within the Pathfinder model. The lower simulation reproduces the behavior of people as seen by the prescriptive code. The codes do not consider different walking speeds of pedestrians depending on age or ability to move. They also work only with zero response time to the alarm. Pedestrians with some disabilities are considered by increasing the width of escape lanes, which is the required evacuation route through the building. So the pedestrian movement is similar to the passengers at the airport on various moving walkways, but with uniform space gaps. This approach makes it possible to calculate the escape routes without any additional technical requirements. This is a very simple approach, and it is compensated by very conservative values, such as the walking speeds. The results are then usually significantly on the safe side. So why do we need pedestrian simulations? The first important application is very complex buildings, such as stadiums. For these types of buildings, the above-mentioned approach reaches its limits very fast. An example is the project of UEFA football stadium, Class 4, which is the best class suitable for Champions League final games, planned for Brno, which we analyzed 3 years ago for the city. On the following animation, you can see the model with 30,000 of visitors. It should be noted that the blueprints were prepared 10 years ago with CAD in only 2 dimensions, so pedestrians move on the flat surface only. We performed simulation tests for the fuel occupancy of 30,000 visitors and showed that the total evacuation time, 95th percentile, is more than 27 minutes, and approximately 1/3 of pedestrians are delayed for more than 5 minutes in the various types of jams during evacuation, as you can see here. This factor is very important for the total evacuation time and a risk analysis in general, but it is difficult to describe it with the classical approach using simple prescriptive codes. On this picture, you can see the distribution of the trajectories. It shows that the longest travels are around 650 meters, which would mean an evacuation time approximately 21 minutes when applying the mentioned prescriptive velocities, which is only 80% of the simulated evacuation time, and this result is no longer on the safe side. The second application is objects or situation, which we refer to as so-called soft targets. The term is used by the security community to refer places with a high concentration of visitors and a low level of security against violent attacks. The attack will cause a situation where the assessment using a prescriptive code is not possible anymore. The reason is simple. The fire safety assessment using prescriptive codes is designed for a case of fire, and in this case of a fire, all evacuation exits will be available, fire alarms will work, and so on. In the case of a terrorist attack, however, the attacker's very basic motivation is to change the situation. A typical example would be a truck blocking one of the main exits or a smoke cartridge thrown into an escape route. For these reasons, it is necessary to perform a risk analysis, identify possible attack scenarios, and determine the impacts of these scenarios. In the case of a scenario analysis, we usually choose a qualitative assessment. This does not make sense to search, for example, the exact probability of a knife attack if it is very rare or never happened yet. On the other hand, the same qualitative analysis is too simple for the impacts of these situations. Instead of qualitative scale, which means low, medium, high, the security manager should request specific data about affected persons, an extension of evacuation time, or reduction of visibility due to smoke, and so on. Simulation tools are extremely suitable for these answers. During the winter months this year, we applied this procedure to the main railway station in Prague, where we tested the evacuation scenarios for the security managers caused by various types of attack. These situations may include, for example, suspected explosive devices or shooter inside or outside of the object. These situations were tested for different occupancy and statistically processed. But the appropriate risk analysis was the first step for identifying these scenarios. Risk identification has the four main phases: asset analysis, where asset is anything which is valuable for us, threat analysis, vulnerability analysis, and determination of the resulting risk. The methods applied in the identification are qualitative, which means probability of occurrence and probability of loss of value, or qualitative, which means determination of vulnerability and degree of threat, or combined semi-quantitative. The risk assessment can be summarized in the following table that reflects a combined semi-quantitative approach. Then it is possible to quantify the risk by using the following relationships to assess and express risk. We should also express how the risks can interact with each other. For this purpose, we can apply quantitative risk analysis with their correlation in the following table. This method expresses the activity or passivity of each risk. Activity means that the selected risk has the potential to cause another risk, while passivity means that the selected risk has the potential to be caused by another risk. The character X means that the fact that it cannot cause by a risk by itself. 1 means the real possibility that the risk on this list can cause a risk on this list, and 0 expresses a situation where it is not possible. For example, lightning, which is a bold line, may cause a high temperature, it means fire, or a tree fall, but it will not cause an icing directly. Then we are able to calculate the following variables of activity and passivity for each of the risks. For the activity coefficient, the sum of the risk, it is the horizontal axis, and for the passivity coefficient, it is the vertical axis. X is the total number of risks. These values can be plotted. It allows us to determine the most significant risks very easily. For better clarity, it is appropriate to divide the plot into segments. We define lines which divide plot into segments, assuming that in the first segment there will be 80% of the most significant risk. These are primary risks with the highest coefficient of passivity and activity together. The described procedure was also applied in the case of Prague main railway station. The results risks analysis was used for the identification of several specific scenarios. Examples include the following: simple evacuation, where all exits are available, an attack in the central part of the station, which means blocking of the central tunnel, an attack at the main exit, or identification of an explosive device nearby. These and other scenarios were then simulated using Pathfinder model to find exact impacts. Results were implemented into the guidelines for security managers. Here you can see the floor plan on the Prague main railway station with the escape routes. The station has the main entrance from Vrchlického sady street, which is bottom, and 6 side entrances. Below the check-in hall, there is a subway station of the line C. Evacuation from the subway takes place using escalators and stairs to the lobby of the check-in hall and then outside. Experimental data, especially the real evacuation trial and long-term empirical measurements, were not available. For this reason, we tried to define the appropriate characteristics, especially the movement speed and pre-movement time, for agents from the related studies mentioned in the references. Here you can see the distribution of movement speeds for different groups of agents: youngsters, adults, and seniors. The pre-movement time was derived using the same sources. The key is to maintain a log normal distribution according to the empirical knowledge. The mean value of the pre-movement time is then about 60 seconds, with a standard deviation about 30 seconds. The values of 5% and 95% quantiles, which means 20 seconds and 120 seconds, were used as the boundary values for the simulation settings in the green region. The initial occupancy is based on the documents for the original fire safety assessment of the building, with the basic value of 6,000 commuters in the building. Our analysis then adds other real occupancies in the range of 1,000 to 10,000 commuters, with a step of 1,000 commuters to cover all relevant daily, weekly, or annual variations. Here you can see the distribution of agents with the density of 0 to 2 agents per square meter, according to the real experience of the security managers. Both the distribution of agents in the station and the distribution of their parameters within the population have a significant impact on the evacuation time, so we use the Monte Carlo approach. The individual scenarios were gradually loaded by increasing occupancy. For each scenario and occupancy level, we ran tens of simulations with a random distribution of agents and statistical distribution of their parameters. We then focused on the following results. The first one is a well-known total evacuation time. This is the moment when the last agent leaves the station. We consider various quantiles like 95% quantile. All is described by graphs and tables. Here you can see my favorite output, which is maximum density map, very useful for security managers. It is displayed as a heat map to find parts of the station where a critical density has formed at any time during the evacuation. The color of the agents on the simulation corresponds to the time remaining until they leave the station. Here you can see maximum time to exit. This output helps to find places in the building from which evacuation is most complicated and where the security manager should focus its actions at first. And the last picture, maximum usage. It shows how long the jam prevailed. The longer the congestion, the higher the frustration of people and the greater the risk of injury or panic. This output should be combined with the density output for the best interpretation. For the client, we also created a flyby in various situations, which can be observed in VR. The security managers are able to check by this way the applied measures. In total, we analyzed 7 different scenarios, each with a capacity of 1,000 to 10,000 commuters. For each occupancy, tens of simulations with random input parameters. This means several thousands of individual simulations. This procedure would not be possible without advanced automation, in our case using scripts in the R statistical language. We modified the Pathfinder input file to achieve the following changes: number of agents, parameters of agents, random seed, to open or close the doors. The results have been processed using the same approach. Besides the third-party software tools, it was also important to deploy computing server. In our case, it was dual CPU Intel Xeon with 24 cores for multi-threaded processing of Pathfinder simulations. Without this platform, it would not be possible to carry out simulation tests in a sufficient time. The soft targets protection is a long-term issue, especially in developed countries, which are the target of terrorist attack and similar threats. The development of simulation tools has enabled a new level of accuracy for the risk analysis applied by security professionals. When applying, we must use the correct approach of risk analysis and interpret these risks in the simulation tools. An example is the occurrence of the shooter outside of the object, which we interpret by closing specific escape routes. Among the simulation results, in addition to the evacuation time, we must also include other outputs that are important for security managers, for example, heat map of time to exit. Further development will depend also on the level of digitalization of the construction industry. A very good example is the building information models, which we applied in another of our studies of soft targets, the Prague subway station. You can see much better visual properties when comparing to the football stadium. Support for the key standards like industry foundation classes by simulation tools significantly speeds up the analysis, makes it less expensive, and enables much more attractive visualization. This will enable us to further replace an assessment through prescriptive codes wherever it makes sense. Thank you for your attention.
Yep, so we have the first question coming in here, just regarding the speed of the agents. How exactly do the agents pick their speed from the predefined range?
I see. As we saw in the presentation, we divided pedestrians into 3 groups, young adults and seniors, and each pedestrian in each group in separate simulations picked the speed from the specific range with the distribution.
So you applied like a uniform distribution or a normal distribution or something like this, and then within that it was selected. And there's a function within Pathfinder for selecting. You can define a distribution of ranges. I think there's normal, uniform, log normal. There's a few different options you have, and it will distribute those.
We used a log normal distribution with the range you can see on the presentation.
Okay. Any other questions? I was just mentioning earlier, you had a nice comment from Eric. Thank you for that in the stage chat. Just every big project should be analyzed in such a complete way. Did you use families or grouping in the evacuations?
No, in this case, we didn't use grouping.
And do you think that that may or may not have a impact on results?
Maybe so, but in this project, we were not so familiar with the grouping, and we didn't perform some tests in the simple cases to be familiar with this feature and to use it with some specific outputs, which can be interpreted by the right way.
Mm-hmm. Yeah, we do tend to see a little bit of an impact from grouping in terms of just generally a slowdown overall of movement, just because the groups try to stay together and people have to avoid, and there's a little bit of a more turbulent kind of flow to the.
Yes, and to be honest, in this situation, in this station in Prague, based on the experience of security managers or the company which run the building, there are only few groups per day which could be observed. For example, from some time to time, some school group or something, but the impact is very, very low.
Okay, great. And then there's a comment here. Was there a way to input a panic factor in evacuation modeling? I think that might have been potentially for somebody else here. They're saying Steve, but maybe it's related to you.
What does it mean, the panic factor?
Yeah, I think that might have been a question for Steve Gwynn. But I will say that there's not, in Pathfinder anyway, which is the tool used here, there's not a like panic mode or a panic trigger, but you can have agents change profiles, which then maybe accelerates their speed or something like that. But that I don't think is included here.
Yes, but as we already know, we had to be very, very careful when using panic on any way during the simulation, because panic means to completely change the behavior, to be selfish, to ignore the rules and so on. And this situation or this behavior can be observed in very, very few cases or few cases.
It happens less often than people imagine, I think. Okay. And good link here from Enrico. I'm not sure. I haven't followed it, but
yes.
Oh, panic. Oh, a little bit panic or not, clarifying the misconception. So
that's
great,
it.
Great link, Enrico. Thank you. Any other questions? Not seeing any. Okay. Well, I think with that, maybe we'll transition over to the next talk. Thank you very much, Tomas, for your talk and your Q&A time here. Really appreciate it. So
thank you.
Take care. Thank you.
Take care.
Bye-bye.